Hello, good evening, sir.
Good evening, sir. Good evening.
Yeah, good evening. So, yeah, welcome to the session, sir. So, let's
Thank
just wait for a couple of minutes for to see whether anyone else is also joining, and then we can start our discussion. So, yeah, by the way, we are celebrating Holi all over India. So,
Yeah,
happy Holi
happy
to
Holi,
you.
sir. Happy Holi, sir.
Yeah. So, do you celebrate Holi over there as well?
Earlier, actually, when I was in Waljad College, so over there, so there were many Indian friends, so I was with them. But in this college, current college, so we don't have actually
Okay,
from North India. Two, three are there from South India, and I don't think they celebrate.
I see. Okay,
Yeah.
sure. Yeah, so basically, I was not able to conduct the session on Tuesday this week because I was not well. So that's why I requested to shift the session to Friday.
Yeah, yeah.
Yeah. So, sir, I think we will get started now because it's already 7:05 now. So if
All
you,
right, sir. All right.
yeah, so I think if anyone else is going to join, so they can catch up later.
Yeah, yeah, sure, sure. No
Yeah.
problem.
Yeah. So basically, I think the previous week's content was related to bond graph modeling. So I tried to solve some problems in that session, and then in this week, so we are basically discussing about the content related to basic system models for different kinds of system. So, basically this week's content focuses on the fundamental building blocks for each types of the systems like mechanical, electrical, hydraulic, pneumatic, and thermal. And so basically the basic building blocks for each of these types of systems. So it's kind of we visualize them as like resistance, capacitance, and inertance for each type of system, and then try to kind of establish an analogy with electrical like its electrical counterpart. So For example, like in mechanical systems, mass is analogous to inertance or inductance in electrical, and the damper, like damping properties, are analogous to electrical resistance. And the spring stiffness properties, like stiffness or elasticity, they are analogous to capacitance in electrical domain. Similarly, we define like hydraulic resistance, hydraulic capacitance, and hydraulic inertance, and similarly for pneumatic systems as well. And in case of thermal systems, we have only two building blocks, like the thermal resistance and thermal capacitance. So we do not define a thermal inertance as such. So this was about like a gist of the content for this week. So my plan is to I have picked up some sample problems related to each of these types of systems, and we'll try to solve them. And yeah, and if you have any questions, so you can bring them up, so related to the course content for this week. So sir, like, do you have any questions, any comments or doubts, anything like that, so related to the course content?
Yeah, so far it's good. I am enjoying this. Though last week class on, I think I missed that class, but I already watched that video, the recorded video that you already uploaded.
Right, sir.
Yeah, yeah. So for me, it is fine. The way you are explaining and the PPTs and the recorded session as very well. And
Okay, sir.
thank you very much for your support and your time and effort, everything.
Sure, sir. Thank you very much. Thanks for your feedback, sir. So yeah, I hope these sessions will help you like to get the course content in general, and I'll also try to bring in some more practical perspectives in terms of, like, like as I said, like showed like a demo with like MATLAB simulations. So I'll also try to show more demos. So like now I think the first few weeks are like establish the basic terminology, the basic theory, the building blocks for modeling each of the systems. Then we actually go into actually modeling practical systems which are like bigger models, where we use these building blocks to be so generally we do not have only a purely mechanical or purely electrical or like that kind of system. So generally we have always a combination of different uh, like systems. So where so all these elements, or most of these elements, may actually come into picture in industry, where we have, like, let us say, industrial machinery. So we will have mechanical components, electrical components, hydraulics for actuations and all those things, like, as well as pneumatic actuation. So all of these things will come into picture, and thermal, as will always be as such, will be present, because there will always be something changing with temperature, pressure, and all these things. So we'll be dealing with at least two, three of these types of building blocks at a time. So in actual practical systems. So yeah, so we will try to see some more demos as we go along this course. So yeah, that's the general idea. So shall we start with the sample problems?
Yeah, yes, sir.
Okay, yeah. So first we will start with the mechanical systems related problem. So we have a spring mass and damper kind of a system here. So here we have like a mass M1. So it has basically like springs attached, K1 and K2 on both sides. And so the mass is also undergoing some friction with the floor. So this is basically the friction. Uh, yeah, so this like basically the where we find like there is a friction between the mass and the floor. So then so basically this is the friction. Then we have these dampers like B2 and then another spring K3 attached. So these system variables are basically x1 and x2. So basically we have to develop the equations in terms of these variables. So then how would we generally start this particular solving this particular problem?
Yeah, we usually make this free body diagram.
Yes, yes, sir. Right. So we first make a free body diagram as you said rightly. So let us draw the free body diagram and show each of these forces. So let us draw the free body diagram of the mass M1 first. So we see that it's given that there is a force Fe acting on the mass M1, which is an external force. Then now it is given that the displacement x1 like is rightwards and like that is the direction of positive displacement x1. So let us assume that the spring K1 is in tension. So the spring force in like K1 will basically be K1 x1. So that will be the force applied by the spring K1. Then we have another spring K2 which will uh, again exert some force on this mass. So now let to kind of assume certain we have to assume certain direction of this force K2 to write the equations of motion. So let us assume for the particular instant that let us say that x2 is greater than x1. So then that would mean that basically the two ends of the spring have been displaced in such a way that the spring will be in tension. So therefore the force exerted by the spring K2 we can assume it to be tensile and its magnitude will be basically K2 into x2 minus x1. So like this we can assume some direction and then write its equation in that way. And then there is another force acting on this mass which is basically the friction force. So let us assume that this is this is the friction viscous friction coefficient. So we will assume that it is proportional to the velocity of that mass which is x1 dot. So b1 x1 dot. So now the second part of the system is basically like the system variable x2 which we are dealing with. So here it is just a junction. So there is no mass actually present at that point. So we can just consider it as a junction. So then the force exerted by the spring K2, K3 and the damper force B2, damper B2, their forces will basically be in like equilibrium. So what we can say is that because there is no particular mass as such at that point, so because net force will be mass into acceleration. but because there is no mass at all, so there will be no acceleration. So those forces will be, so we'll just draw the free body diagram to indicate like the directions and magnitudes of these forces which are acting at that particular point. So now because the spring, like the spring force, uh, the spring force now because this x2 is rightwards and this so therefore we can consider that this spring k3 is in compression. So therefore the force acting on the this point will be basically k3 x2, and then similarly the uh, so we'll assume that the direction of the velocity is also right towards the right, so then the force exerted by the damper will be basically b2 into x2 dot. So these are the forces which are involved in this particular system here. So so then now what would be the next step? And yeah, before that, so is are we missing on any force? So I think we have
Uh,
considered all the forces, right?
all forces are included now.
Ah,
Yes.
yes, sir. So yeah, so what would be the next step now, sir? Uh,
Now the next step is sum of all forces will be equal to zero. So on each body here. So for example, on mass m1 we have Fe in left to right. So Fe minus k1 x1 minus b1 x1 dot is equal to k2 x2 minus x1
yeah, so like, you're right, sir. So though, like
with
basically
minus.
we'll equate the sum of forces to mass into acceleration basically. So we'll apply Newton's
Yes,
second
yes.
law.
Yeah, yeah.
So
Correct.
so we'll apply Newton's second law, and so we'll write, so the sum of the net forces would be, so Fe,
Fe minus k1 x1 minus b1 x1 dot and plus k2 times x2 minus x1.
yeah,
That will be equal to m1 times x1 double dot.
Fe minus K1 x1 minus B1 x1 dot. So this will be our first equation of motion. And
Yes.
then similarly, our second equation of motion, so we can write it as, uh, so all forces in minus, yeah. So K2 x2 minus x1, K3 x2 and B2 x2 dot. So these will be the two equations of motion. So we can basically rearrange them, and then uh, to solve this equation, so we can rearrange these terms and then use some numerical methods, and or we can also use some analytical methods if possible, so to solve this particular equation. So but this week we'll not be discussing about how to solve these equations, so we'll be looking at that aspect later. So right now we are just looking at how to use the basic fundamental laws of physics to derive the differential equations for any particular system. So this was the procedure for this kind of a mechanical system. So is that fine, sir? Any
Yeah, yeah,
question?
it is clear. It's
Okay.
clear.
Yeah. So then we can proceed to the next uh, problem. Yeah. So yeah, the next question is like a multiple choice question. So as I just mentioned, so like there will be like we try to establish analogies. So we basically look at the forms of the equations in for any system, and then try to write, like identify which quantity is analogous to which electrical quantity. So yeah, one thing is there that the damper is analogous to electrical resistance. So now only thing is that which it's like analogous to which form, so whether it is R or 1 by R, minus R or minus 1 by R. So that is being asked here.
So I think in a force current analogy, it is analogous to, I think, R, and but here it is in force current analogy. So it will be 1 by R.
Yeah, so for a electrical, so in electrical thing, like we write that I is equal to V by R, and here force we write it as, let us say,
Force.
C
Ma,
into
yeah,
X dot,
dot, yes.
right? So then force is analogous to current. So like force is analogous to, let us say, current, and then let us say like the velocity x dot is analogous to voltage here. So then what remains is the damping constant. It will be analogous to then 1 by
1 by
R.
R.
1 by R.
Yes.
So so then the correct answer would be this. Yeah, it actually seems a little bit strange that, like, velocity and voltage are like somewhat analogous, but physically they may not really make sense as such. But yeah, so it's basically based on the form of the equations as such.
Hmm.
But yeah, in general, like qualitatively, we can also understand that damper is something that is like a resisting force which provides a resisting force, and electrical resistance is also something of the same type which dissipates energy. Damper also dissipates energy, so they will be analogous. The specific form of the equation, it just decides like whether it is R or 1 by R. So here it's 1 by R. Sorry, I think there was some. Yeah. So the next problem is about thermal systems. So we have been given that heat is being conducted through a zero point 0.2 meter thick industrial furnace wall made up of fire, clay, brick. So let us just draw like a wall. So it is given that there is like the wall is zero point 0.2 meter thick. So the wall temperatures inside and outside of the furnace. So let us say that this is the inside of the furnace. So this is 1100 Kelvin, let us say. And then this is 1500 Kelvin. So the length of the wall is 1.2 meters. So like we will draw the side view. So it's basically like this. So this is 1.2 meter if we look at it from the side, and the height is 1 meter, and this is, let us say, 1.2 meters. So this is the side view, and let us say this is the front view. So it has been given that the thermal conductivity for the fire clay brick is something like 1.7 watt per meter Kelvin. So we have to find now the heat conducted through the furnace wall. So yeah, so we have been basically given the dimensions. So we know the area of cross section across which heat is flowing, and then we know the temperatures on both the ends of the wall. So now how do we solve this particular problem now?
I forgot about this concept actually.
Okay. So yeah, basically we have to just apply the simple like Fourier's law of conduction. So uh, so so what it says is that the heat flux So we can write it as which is flowing across any particular cross section. So that is directly proportional to the temperature gradient. So and the constant of proportionality is the thermal conductivity. So as we know that heat flows from higher temperature to lower temperature. So uh, so that's why it's actually flowing opposite to the direction of temperature gradient. So that's why we have the minus sign. So let us say that the wall temperatures, like if they are T1 and T2, and if, like, T1 is greater than T2. So if T1 is greater than T2, then we can write that. So the heat flux will be basically K into, and if that, let's say, L is the thickness. So if L is the thickness, then we can write as K into T1 minus T2 by L. So in this case, we have been given, so that uh, so the thermal conductivity is given, the temperatures are given. So we know that the ends of the two walls are at 1500 and 1100, and we know the cross-sectional area. So area here will be 1 into 1.2. So basically 1.2 square meter. So this will be the area across which the heat is flowing. So the heat flux will be basically Q by the area, the heat flow. So the heat conducted is something that we need to find. So that's why then we will, so to find out the heat flow, we will multiply this by area. So this will become, so the heat thermal conductivity is 1.7, and then we have the area, which is we found it as 1.2 into temperature difference, which is 1500 minus 1100 divided by the thickness, which was given to be zero point 0.2. So this we can calculate it. um, So we get the answer as 4080 watt. So is that calculation correct?
Yeah, yeah, it's correct.
Okay. So yeah, so this is basically the simple conduction equation that we can apply to solve these kind of problems. So then the next question is about, it's based on the same thing, but now we consider it in terms of thermal resistance. So let us say we have a some wall which is made up of different composite materials, like, so as we have in any general wall. So we we have the bricks and concrete layers, like cement and brick layers. So then the materials, because of the materials being different, so then the thermal conductivity of each of them will be different. So then so the heat flow through each element will be different. So we can basically try to estimate what will be the total thermal resistance based on the material properties. To find the numerical value of the total thermal resistance, we need the specific values of the thermal conductivity of each material. So I think it's not given here, but let us assume that thermal conductivities of each material. Let us say this, we will assume it as Ka, Kb, Kc, and Kd. So the cross sectional area for the material A, let us say AA, so it's given to be 10 centimeters. So it's 10 centimeters width, and height is 3 plus 7, which is again 10 centimeter. So 10 into 10, so it's 100 centimeters square. And the thickness of the material A, so it is given as 3 centimeters. So the general expression for thermal resistance is basically L by K into A. So where L is the thickness, K is the thermal conductivity, and A is the cross-sectional area. So likewise, we can use the this particular equation to calculate the thermal resistance for each of these components of the wall. Similarly, the thickness of materials B and C are both same, so it is 8 centimeter, and then the cross sectional area of material B is 3 by 10, so 30 centimeters square, and cross sectional area of material C is 7 into 10, so 70 centimeters square. And so the cross sectional area of material D is also same as material A, so which is 100 square centimeter, and the thickness of material D is 5 centimeter. So like this we can apply and calculate the resistance for each material using, so by dividing the L by Ka for the respective material. So I will not write that, so I have just written L by Ka, so then we can apply the same thing for each of these materials. So let us say we calculate the each of these resistance as RA, RA, RB. RB and all those things. So now the uh, now we have to find out the total thermal resistance. We need to, so how do we find the total thermal resistance in this case? Any idea?
In this case, I think we need to see how the heat is flowing, whether they are in series or in parallel. So using
Exactly.
the concept.
Exactly. So basically we need to construct an electrical equivalent circuit kind of thing. So so here like the temperature at each of the ends will represent, it's analogous to voltage, and the heat that is flowing is analogous to current. So then we can draw like an equivalent circuit. So let us say, so this is, let us say our first node, which is at, let us say 400 degrees Celsius, and so the first layer is material A. So we can write down the resistance as RA. Now the interface between materials A, B, and C, so we can just write it as some node, and then so we can observe that the B materials B and C are stacked over each other. So the heat that is flowing through material A will be distributed between B and C, but the ends of, like the two ends of B and C material, they are at, like the temperatures are same at both the ends. So then we can write them in as though if they are in
Parallel.
parallel. So we can show them as resistances in parallel. And now the third layer is again in series with these. So and this is at 60 degrees Celsius. So the current, so instead of current, so we will write it as some Q. So that Q will be distributed across B and C, and then again that same heat will flow through resistance RD. So this is how we can construct the equivalent circuit. Sorry, so then now we know, like we can use the same method, like the electrical resistance calculation methods. So we will first calculate the equivalent resistance of B and C. So because they are in parallel, so so we can simplify it so as RA. So I'll just say that this is, I'll call this as RP, let us say, and then RD. So RP will be equivalent of, so equivalent resistance in parallel, we can use this formula for calculating the equivalent resistance here. So yeah, so this is the uh, equivalent resistance, and then since these resistances are in series, so it will be basically RA plus RP plus RD. That will be the total thermal resistance. So let us say R total will be RA plus RP plus R2D. So this is the total thermal resistance that we can find out. So the specific for the specific numerical values, we will need the thermal conductivities also. So which is not given here. So but yeah, so if you are given those values, so you can easily calculate the thermal resistance in like, numerically. So that I think is easy to do. But yeah, the general method is like to draw an equivalent circuit and then try to use the same method like an electrical resistance to find out the total resistance. So is that okay, sir?
Yeah, yeah, it is fine. Yes.
So yeah, so the next question is about hydraulic capacitance. So basically capacitance basically means storage of some energy. So in what form? So in case of hydraulic capacitance, so the energy is stored in the liquid in what form?
It is potential energy.
Yes. So yeah, it is in the form of potential energy. You're right. Yeah. Next again we have another mechanical system here. So we can again use the same approach like the earlier one. So just to like we'll just draw the free body diagram and then show the forces and use the Newton's second law. So that's the general procedure here as well. So let's start with the free body diagram. Now here we have been given the coefficient of friction as B1. So we will show this force as B1 x1 dot, and then since the motion of the mass m1 is towards the left, we will show the spring is in tension, which is k1 x1. So now in with for the spring, so one end is connected to the pulley, and so let us say there is a tension T1. Now because this spring, if we assume it to be massless, then in that case k1 x1 will be equal to tension T1. Otherwise, if it is not a massless spring, then the tensions on both the ends will not be the same. Now for the pulley again, we have like tensions T1 and T2, let us say on both the ends. Now because we have been given that the pulley is ideal, so which ideal means that it is frictionless and massless. So if there is no friction, so then definitely T1 and T2 will be equal, and also because it is massless, so there will be no energy basically being so there is no basically there is no mechanical energy that is being carried by the pulley as such. Now and because it is frictionless, the tensions on both the ends will be equal. And then for the mass m2, so For the mass M2, again we can draw this free body diagram here. And since it is moving downwards, so basically the spring K2 will be in tension. So the spring force we can write it as K2x2, and the damper force, and because it is moving downwards, so damper force will be actually upwards. So which will be V2 into x2 dot, and the tension T2 will be acting here, which is actually equal to T1, which is equal to K1x1. So these are the free body diagrams uh, for the all the masses. And if the pulley was not like not massless or not frictionless, so then we will have to write down the the equation for torque due to friction. So basically the torque that is created because of the friction in the pulley, and so that will be, and depending on the angle of wrap, so if the pulley is not frictionless, and depend so then depending on the angle of wrap of the rope over the pulley, that will decide how much will be the the difference between the torque, the tension on both sides. Yeah, so any questions, sir, like till now?
Yeah, it's fine. Clear.
So then we can just proceed with writing the equations of motion now. So let us
Yes.
first start with writing the the Newton's second law for mass m1. So the force acting is Fa. Now because the convention given here is that leftwards is positive, we will stick with that convention here. That we'll assume the forces which are acting towards the left as positive. So therefore we'll write Fa as positive, and all the other forces are acting towards the right. And similarly for mass m2, k1x1 minus k2x2 minus k2x2 dot is equal to m2 x2 double dot. So these are the two equations of motion for the system here. So this is how we can write down the equations of motion for any mechanical system. Just use the simple Newton's second law and draw the free body diagrams and write the equations of motion. So that's the general approach. So now next we come to the uh, this electrical circuit which is given here. So we have to find out the mathematical equations for this particular circuit which is given here. So how do we generally solve these kind of problems?
To solve these problems, we can use circuit analysis methods like nodal analysis or mesh analysis method we can use, or we can simply calculate voltages at different nodes, and then we can use KCL KVL also. Simple.
Right. Yeah. Yeah, I think the simpler ones are just as you said, like is Kirchhoff's voltage law or Kirchhoff's current law. So those are the simple like ways to like solve this. So we can add so either consider like Kirchhoff's let us say let's consider like for Kirchhoff's voltage law for these two loops here. So the so let us consider the loop. Let us like label them as A, B, C, D. So let us write down the for loop A, B, C, D. So we'll sum up the potential difference across each component, algebraic sum of those, and then equate it to zero. So first we have the voltage EI, uh, so that's being supplied at the between points A and D, and then so we as we move in the direction of the current, there will be a potential drop. So across the resistance, there will be a potential drop that is basically I1 R1. And now here the next component is the inductor L. Now because the inductor is part of both the loops ABCD as well as BCEF, so then we need to consider the net current which is flowing across this inductor, so which is the algebraic sum. So now the direction of the uh, for the loop I1, so that current will be flowing from B to C, whereas the current I2 for that other loop is flowing from C to B. So therefore the net current that is flowing through inductor L will be I1 minus I2. So therefore the potential drop across the inductor from B to C will be L into d by dt of the rate of change of current flowing across the inductor, which is I1 minus I2. Then similarly, if we write the equation for the other loop, so then we can say so minus I2 R2. So if we move from B to E, so there will be a potential drop if you go in the direction of current, and then the potential difference across the capacitor. So will be basically uh, so voltage across the capacitor will be so EO, which is given here, and so that EO we will write the specific form of that, and then as we go from uh, so let us say the net conduct as we assume that the net direction of the current is from, let us say, B to C for the inductor. So then if we are traversing the loop from C to B, then we are going in the direction opposite to the current. So therefore, the potential difference will be, so there will be a potential rise, not a drop, because we are going against the direction of current. So that will be L d by dt of I1 minus I2. So now EO is the voltage drop across the capacitor. So EO, so it's basically the charge stored in the capacitor divided by the capacitance. So the charge stored will be integration of the current that is flowing through the capacitor, which is I2. So that is the voltage drop across the capacitor. So this is for, so this is for this loop BFC. So yeah, so this is the like the way we can uh, write the the equations. So similarly, we can also use Kirchhoff's current law. So for that, we basically use we basically we'll identify the junctions like B and E. Let us say B, the junction B. So so the current I1 can be written as, I1 can be written as VA minus VB upon R1, and the current flowing across from B to C is I1 minus I2. So which is, similarly I2 we can write it as VB minus VE upon, and we know that since the potential VD and like the point C, D and F are equipotential, so and we know that the potential drop across like V, so VB minus VC is, So using these equations, so we can now write the equations. So we can substitute the expressions for I1 and I2, and then uh, derive the simplify the equations further to get again the equation of motion in terms of the given variables. So any questions, sir, till now? So if not, then we'll just continue with the next problem.
Yeah, yeah, sir. It's fine, fine, sir.
Yeah.
Yeah, yeah, okay.
So yeah. So the next question deals with heat transfer. So it is given that a wire which has some diameter and length, it is submerged in water at atmospheric pressure, and electric current is passed through that wire. So we will show this. So the water will be boiling at 100 degrees Celsius, and so the heat transfer is through convection, and the heat transfer coefficient is also given. So we have to find out the uh, power that is being supplied to maintain that the temperature of the wire surface at 120 degrees Celsius. So the wire is maintained at 120 degrees Celsius. So the wire has some diameter and length. So and heat is being transferred through convection to the water. So the heat transfer coefficient is given as 4500 watt per meter square degrees Celsius. Now what will be the surface area of heat transfer? So the so now
Sir,
the
surface. Yeah, okay. So it will be pi total area 2 pi d into length of this
right,
wire.
right. So the if the diameter is d, so the area, so basically heat transfer will be equal to area into the heat transfer coefficient into the temperature difference. So here it is 120 degrees Celsius. So let us call it as T wire minus T uh, water. So area is the curved surface area of the cylinder, so which is pi into diameter into length, and which is equal to, So this much of millimeter square area, and so this is the area, and then so the heat flow will be 4500 into 706.858 into, since it is millimeter square, so we will multiply by 10 to the power minus 6 to convert it into meter square, into temperature difference, which is 120 minus 100, we should ideally convert the temperature into Kelvin and then uh, subtract, but it's anyway we are just concerned with the temperature difference, so it doesn't matter so whether it's we are subtracting in Kelvin or degree Celsius, because Kelvin and uh, Celsius are just linearly related. So the value comes out to be 63 point what. So this is the answer that I'm getting. Is it the same answer that you are getting? So I think yeah, we will I think we'll get this answer itself. So you can check, basically it's just simple numerical calculation. So so now yeah, we have another mechanical system example, and yeah, so then I also have some examples on electrical and hydraulics and pneumatic systems. So I think yeah, maybe we'll cover one more example of mechanical systems, and then yeah, so you can, so there are many other problems which I have in the list. So if you are not able to cover them in today's session, so you can actually try them on your own. And so yeah, if you are not able to solve anything, like, then we can discuss it in the next few sessions. So yeah.
Yes, 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 sir.
Yes. Yeah, so first again, so here in this, like, this is being a mechanical system, so so we'll use the same approach here, like draw the free body diagram and then show the forces. And yeah, so here it's basically this thing is hinged here. So we'll assume that this is like a hinge. So then this mass is moving up and down. So so we will show the, let us say, if let us assume that the mass is deflected by some angle theta. So the force acting on the masses will be basically the weight. Now since the mass has moved downwards, so the spring force will be, so k into delta some deflection delta, which will depend on the location of the this point. So it will depend on A and the angle of deflection. And let us say C into some delta dot, and let us say the, so the deflection from, let us say, from the equilibrium position for this mass is, will be, let us say, some x or y or whatever. So then so from basic trigonometry we know that this value delta is a nearly equal to a sine theta. So and the velocity of this point will be
It will be a cos theta.
del so if we differentiate this delta with respect to time, so we will get a cos theta into d theta by dt.
D theta, yes, yes.
Yeah. So similarly, y will be, so basically it will be the L sine theta, and y dot will be the velocity, which is again L cos theta into d theta by dt. Now if we assume that theta is small, so if theta is small, then sine theta is nearly equal to theta, and cos theta is nearly equal to 1. So then we get basically a sorry. So we get delta is a theta, and delta dot is a theta dot, and y is again nearly equal to L theta, and y dot is nearly equal to L theta dot. So these are the approximate equations for small angles. So this was the kinematics basic part of that, and then now we will write the Newton's second law for this system. So for that we can either use the like either the moment equation or the uh, or like we can use either the energy type of approach, or we can use the either the simple Newton's second law type of approach as well. But yeah, so we can just like use the like take the moment about this particular pivot and write down the moment equations. So we take the moment about pivot or hinge basically. So that will be, so the weight is not a dynamic force, so we will not consider it in our moment equation, because uh, that will just cause a static deflection in the spring. So apart from that, so if we take the measure the displacement from the equilibrium position, so then we will basically the static deflection and the weight will just cancel each other. So and then the deflection measured from the equilibrium position is the will cause basically the dynamic variations of the spring force and the damping force. So yeah, so the moment about the hinge will be caused only because of the spring force and the damping force. So the moment about the hinge for uh, the spring force. So basically it is K into delta, which is A theta into A, and similarly for C into A theta dot into then A. So these are the moments. So because they are in clockwise direction, so anti-clockwise direction, we will consider them as positive. And since the mass has deflected downwards, so which is clockwise theta, so then so we will take the, so which is basically, so I theta double dot, and since because theta is clockwise, so we will put a minus side here. So the I is the basically moment of inertia about the hinge. So let us assume that the if the rod is massless, so it's basically the rod plus the moment of inertia of that mass m. So if rod is massless, so then this term will be 0. So the moment of inertia of the rod is 0. So this will be 0. And the moment of inertia of the mass about the hinge will be mass into the length, like the distance from the pivot squared, so into m into L square. So then the equation of motion becomes Ka square theta plus Ca square theta dot is equal to minus m L square theta double dot. So this is the equation of motion for this, for small oscillations. So any questions? Any questions on this?
No, sir.
Okay. Yeah. So then we will proceed to the next problems. Yeah. So this is an interesting problem. So
Yes, sir. It will be 5 upon 200.
yeah. So how did you calculate that?
Yeah, actually, under steady state condition, this inductor it behaves as a short circuit.
Right.
The capacitor behaves as an open circuit. So therefore, it will be having only resistance R1 and R2 in series, and voltage source is 5 volts. So R1 is equal to R2 100, both 100. So total current I therefore will be 5 upon 200 kilo in milliampere. It will be in milliampere.
Yes. 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 You are absolutely right, sir. Yeah. Exactly. So as you correctly said, so the potential difference across the inductor is basically L di by dt, and at steady state di by dt will be 0. So the potential difference across the inductor will become 0, and for the capacitor, so current flowing through the capacitor is C into derivative of the change of the potential difference across the uh, capacitor. So at steady state, this d by dt of this potential difference will become 0. So therefore current across the capacitor will become 0. So therefore, so this capacitor will behave like a open circuit, and inductor will behave like a short circuit. And so the current flowing through steady state will be only through the resistance. So it will be basically V upon R1 plus R2, because R1 and R2 are in series. So which is 5 upon 100 plus 100 kilo ohm. So it's basically, so it is 2.5 into 10 to the power minus 5 ampere. which is 0.025 milliampere. Yeah. So we can prove the same thing by actually deriving the equations and then solving for them, like deriving the equations of motion, and then if we plot the the graph, so we will actually get the same result. But yeah, so this is like the easier way to solve this thing. This is another like mechanical system example. So I think for the rotational system, but I think you can try it on your own. So I think we have discussed a lot of mechanical system examples. So we can maybe quickly go over. Yeah, so we have the hydraulic system example. So yeah, so we can try this particular example first now. So yeah, so here we have been given like there are two containers uh, where there is a constant head supply. So there is, let us say there is a flow, excuse me. So constant flow rate at which Q1 at which the liquid is being supplied, and then the liquid levels in the two containers are H1 and H2. So we have to just basically find out the relationship between height H2 and time. So now how do we go about solving this problem?
In this case, uh, as I studied, this wall is behaves like a resistance,
Resistance.
and this tank will behave like a capacitance.
Correct. Yes.
So, like Q1 minus Q2 will be equal to C times dH1 by dt, and Q2 is equal to H1 upon R, something like this.
Right. So exactly. So you are right. So these are the two main elements. So because we have been asked to neglect inertance, so then so the two other elements that as you mentioned, capacitance and resistance are something we need to consider. So for the resistance R, the let us call uh, let us label this like the atmospheric pressure. So both the containers, let us say, are exposed to atmospheric pressure P naught. So the pressure at the one end of left end of, let us say, the valve, it is will be P naught plus rho g H1. So let us call it as pressure P1, and pressure at the other end of the valve will be, so in the other end of the container, so that will be P naught plus rho g H2. So let us call it as pressure P2. So by the definition of the hydraulic resistance, so we define it as pressure difference is equal to hydraulic resistance into the flow rate across it. So, um, so P1 minus P2 will be basically rho g H1 minus rho g H2, which is R into Q2. So basically we get the expression for Q2, which is rho g H1 minus H2 upon R. And now by the definition of the hydraulic capacitance, so for hydraulic capacitance, uh, so by the definition of hydraulic capacitance, we can write that the so for let us say the container Q, like the container first one, so we can write it as Q1 minus Q2. So it is the net flow entering minus net flow leaving. So that is the capacitance C1 into rate of change of pressure across the two like the so here the one end is exposed to atmospheric pressure, and the other is the lower side is basically exposed to pressure P2. So then so C1, and the capacitance C1, we can write it as, so how do we define the hydraulic capacitance? What is the like general expression for hydraulic capacitance?
For hydraulic capacitance, uh, it is analogous to like I is equal to C dV by dt.
Yes,
So yeah, so same way we can write this
right,
yeah.
right. So then therefore Q1 minus Q2 will be a, so let us say the area of container, area of cross section of container A, it is first one is A1. So A1 by rho G into uh, so rho G will come outside the differentiation. So it will be basically dH1 by dt. So the equation becomes Q1 minus Q2 is equal to A1 dH1 by dt, and then for the second tank we can again write the equations for its capacitance. So now here there is no flow leaving out of the container, so there is only flow coming into the container. So here we will write only Q2 minus 0. Basically there is no flow leaving the container, so it will be C2 into the pressure, rate of change of pressure across this. So C2 we can again write it as A2 by rho g. So rate of change of so yeah. So this will be the equation for the rate of change of uh, dH2 by dt is equal to Q2. So now we have expression for Q2. So from the resistance, the hydraulic resistance. So Q2 is rho g H1 minus H2 by R. So we will substitute it here. Rho g H1 minus H2 by R. So therefore, E2 dH2 by dt plus rho g by R H2 is equal to rho g by R H1. So this is the equation of rate of change of the height H2. And we already have the equation for rate of change of height H1. So which is Q1 minus Q2 is A1 dH1 by dt. So we can substitute again the value of Q2, which is rho g H1 minus H2 by R is equal to A1 dH1 by dt. And again we can rearrange these terms left hand side or on left hand side or right hand side accordingly, and then so basically these are the two main equations of motion for this system. So is that okay? So, any questions?
Yeah, it's fine, sir.
Okay. So yeah, we have another one more question on hydraulic tank. So So yeah, again it's like very similar here. It's just one tank and has two outlets. So Qi is the input flow, and then so the pressure. So let us say the air pressure here is P0. Here it is also P0. Here it is also P0 atmospheric pressure. Then the pressure at A will be basically P naught plus rho gh. So the hydraulic resistance equation, we can write it for the resistance R1 and R2. So that is basically PA minus P naught, or atmospheric pressure, is equal to R1 Q1, and similarly PA minus P naught, sorry, R2 Q2, so which is rho gh. So basically Q1 is rho gh by R1, and Q2 is rho gh by R2. So we get the flow rates in terms of the height and the hydraulic resistance. So now then we can apply the capacitance, hydraulic capacitance equation. So the net flow rate entering and leaving the system, so that is Qi minus Q1 minus Q2 is equal to, so the capacitance into d by dt of Pa minus P0. So we'll just substitute from what we derived for Q1 and Q2. So and pressure Pa is equal to again rho gh. Pa minus P0 is rho gh, and capacitance C is A by rho g. So therefore this equation will become Qi minus rho g h into 1 upon R1 plus 1 upon R2 is equal to A by rho g into rho g dh by dt. So rho g will get cancelled. So yeah, so this will be the equation A into dh by dt. So this will be our equation for this particular hydraulic system. So is that okay, sir?
Yes, sir, it is also fine.
Yeah. Now we'll cover another example of like pneumatic system. Yeah, so while we define the capacitance of a pneumatic system, so it generally has two parts, right? So it is given that the pneumatic capacitance due to change in volume of the container is C1, and because of the compression of the gas is C2, and the mass flow rate entering the container is M1 dot and leaving the container is M2 dot. So then what will be the expression? So among the options, we have to find out which is the uh, correct expression for the capacitance.
In this case, I think the answer will be C. E1 minus B2 is equal to 1 upon C1 plus C2
Yes,
integration 1 dot minus M2 dot.
yes, yeah, you're right. So the capacitance is a combination of the both the effects. So it's because of the either change in volume of the container and also because of the compression of the gas. So because the fluid is also compressible, so that will also contribute to the capacitance. So and it is proportional to the the difference between the mass flow rates. So it is M1 dot minus M2 dot integration of that. So that's the correct option C. So yeah, so now I think we can do one more example of this pneumatic systems. So we can try this. Uh, so we have been given these two containers. So it has so the capacitance of the containers are Cg1 and Cg2, and so there is a fan which is driving the air into these containers. So the output pressure PO is PO inside the container, and the input pressure is PI because of the fan. So now, similar to the hydraulic system, we can just apply the they have same kind of approach like hydraulic, like we derive uh, like the hydraulic resistance. We consider the pneumatic resistance here. So we have two valves, or what they call it as duct losses here. So RG1 and RG2. So we can model them as pneumatic resistances. So so for RG1, we can write it as Pi, which is the input pressure, minus P is, so we'll assume that this QMI or QMO, whatever, that it represents the mass flow rate of the air. So so that will be RG1 into QMI. So that is the for the pneumatic resistance RG1. Similarly, we can write the expression for the other pneumatic resistance Rg2 into QMO. And now we can write down the expressions for the capacitance of the containers C1 and CG1. Uh, Now here, because the uh, container volume, let us say if it is fixed or whatever, like but uh, so let us say we assume that CG1 represents the total capacitance here in this case. So we will not really split into the two parts, like basically because of the volume change of the container and the because of the compression of the gas. So we'll assume that CG1 and CG2 represent the total capacitance of each of those containers. So what is the uh, definition of the pneumatic capacitance? It's basically the difference in the mass flow rate. So here it is QMI minus QMO is CG1 into dP by dt. So rate of change of pressure P here in container CG1, and then similarly we can write down the expression for the other container CG2. So here there is only QMO which is entering the container here. So it will be QMO minus 0. So there is no mass flow that is leaving the container. So it is QMO minus 0. It is CG2 into dPO by dt. So we can use these equations and like basically rearrange them. So it's just algebraic manipulation now to derive the final equation. So then we will basically, we already have the equations of this pressure P, and so pressure P is given by this equation. So we can derive the expression for. So using the first equation, so P is equal to Pi minus Rg1 into Qmi, and Po is P minus Rg2 into Qmo, which is Pi minus Rg1 into Qmi minus Rg2 into Qmo. So now we got the expressions for uh, the pressure P and PO, and now we can substitute these equation like into, so we have the expression for like dp by dt. So that is, so we can substitute the value of p in this equation. So let us we number it as, let us say 1, 2, and we number this as 3, and this as, this let us say we number it as 4. So we basically just need to substitute from 3 and 4 into 1 and 2, and we will get the final expressions for the equation in terms of uh, the pressure, rate of change of pressure, dp by dt, and the flow rates. So yeah, I think that you can I think work out on your own and try that. So I think it's already, I think we are at the end of today's session time. So yeah, so that's what like uh, I think we can conclude our session for today over here. So there are some more problems which I have in the sheet here, but yeah, so I think we can stop here for today, and then you can try those problems on your own, and like if there is any difficulty, so you can just you can either like contact me like over email, so you can write to me if there is any difficulty. So this is my email address, so you can like write to me on this email address if you have any difficulty. So yeah, so that's all that I had from my side for today. So yeah, so if any
Thank,
questions, comments, sir? Yes,
thank you, sir. Thank you for your time and effort. I will try these problems, and in case I feel any issue, so definitely I will email you. Thank you very much.
sure. Yeah. Thanks, sir, for joining the session, and I hope these sessions help you. Uh, yeah. Once again, thanks a lot for joining, and happy Holi. Yeah.
Same to you, sir. Same to you.
Yeah.
Thank
Thank you. Yeah. Bye. Good night.